I will take it on a different note. I will present you some results over the whole continent of Eurasia instead of one city. I want to comment on this. My model results include model results of a regional climate model. So it's not able to resolve the urban scale, even we're here on an urban climate conference. But I want to use the results I got here to go further in the future with higher resolution models to obtain this for example, intra-urban variability. So as you know, we will have more frequent and severe heat waves. And I was wondering during I was doing climate simulations how this will affect our lives. And for this, I came in, on the topic of outdoor thermal comfort. So after I run the model over this big domain over Europe and Asia, I selected some densely populated locations, and for these grid points, I wanted to compute the outdoor thermal comfort. So the model is a model that has a spatial resolution of 25 by 25 kilometers, so not resolving the city scale. And the reason why I want to present you here the results of our regional climate model, Alaro, is because I have learned some things and I would like to share that with you. So first of all, if you run a model, you always have to evaluate and see how well it's doing it compared to the reality. So for that, we couple the model to ERA interim, because back in the time, ERA 5 was not existing yet. And so I took for 58 grid points the data that was needed to compute the globe temperature, the mean radiant temperature, and from that you can compute multiple outdoor thermal comfort indices. And I picked the Universal Thermal Climate Index because with this data I could compare my results to the ERA 5 heat data set that's available recently. And after this evaluation, I wanted to have a look how this would change in the future under different warming scenarios. So for this, we coupled the regional climate model to a global model to have the effect of the global warming. And I chose scenarios where we go to 1.5, 2 degrees, and 3 degrees global warming. So what we do is we look when in the future the global model will reach the 1.5 degree, for example, and then we take a 30-year period around that 1.5 degree moment, so 15 years before and 15 years after. And then we subtract the future result with the historical result to see the change. But before I take you to my results, maybe it's good to have a look at the outdoor thermal comfort these days. So you can see on this graph that in the north there is much more cold stress, and near the equator there is already quite some extreme heat stress for some locations. And on this slide, you see 4 locations indicated that I will present further because there were just too many locations to put on one slide and it wouldn't look great. So if I have a look at the evaluation, then we see that for multiple locations, the temperature and the other variables are simulated very well. So here you see the diurnal cycle. You nicely see that during daytime it's much warmer and during nighttime the temperature goes down. And you also see that for some locations the results are better than for other locations. And this is inherent to a model. It's not able to model everything perfectly. And you can also see that I compared to ERA 5 land, because when I had a look at the ERA 5 data, for some grid points you get some strange things in the curves, and it's a known feature of ERA 5 that if you just look at one grid point, that there might be some disturbances. Then I also had a look at the difference between the hourly and 3-hourly data. And from this, I learned that it's important to have a look at the high frequency, because if you look at the 3-hourly data, you see that the extremes are not represented that well as in the hourly data, which you can expect. So for the climate modeling community, I would really recommend to store also hourly data. However, this is not always possible because it's taking huge amounts of storage. Um, and so if you only store 3 hourly data, please also just store the minimum and the maximum. So then when I had a look at the evaluation for the UTCI, which gave very similar results to the mean radiant temperature, then I saw that something that I didn't really expect because, for example, for Riyadh and Beijing, I got very good results for the evaluation. But then when I looked at the UTCI, I saw that the model, so the dotted line, didn't represent as well the line from ERA 5, the full line. So here you can see the different colors indicating the different seasons, and the black line is the annual mean. And as you see, the range is mainly an issue. So the model seems not to be able to capture the full diurnal range. And this is probably due to a difference in the calculation method of the mean radiant temperature. So for my hourly data, I didn't have all the radiations fields that were stored. So I had to find a way to compute the mean radiant temperature in a different way. So I used the globe temperature, so based on the formula of Sophia Thorsen. Um, and this is an approximation. And this approximation doesn't seem to give the same results as when you use all the radiation fields. So to have a better look onto that for the 3 hourly data, I do have the radiation fields. So now, just before the conference, I started to compute the 3 hourly data as well. And I want to see if this gives me better results than the hourly data. So even though this evaluation wasn't as great as I was expecting, I still wanted to give you a sneak peek of what we can expect because here you can see the diurnal range is not completely captured by the model. So the only thing we have to take into account is that we can expect more extremes in when we look at the difference between the future and the historical. However, when I look at this change in the UTCI, then I see that the strongest cold stress is appearing for all locations. So if you have like global warming of 3 degrees, you will really expect a big change for the whole continent. And on the opposite, we also expect more heat stress for all of these locations. However, it's not a same increase or decrease in cold stress for all the locations, but I will show you in one of the next slides what we can expect. So also, the more the global warming, the more pronounced the changes. And when I had a look at the density distributions of the UTCI, then I saw that we really get like similar distributions as for temperature, so as presented in the IPCC as well. So the distribution is really like shifting towards warmer conditions, and also the variance is changing. So we get more extremes. So when I just have a look at these extremes, so don't take it for granted because, as I said, the model has its limitations. I just wanted you to show you like what the difference could be between 1.5 degree warming and 3 degree warming. Then we see that in the northern locations, there's really like a big drop in the extreme cold stress. And you can see like for, so the bars indicate like the 1.5, in the middle the 2 degree, and the most extreme change for the 3 degree warming. And then near the equator, so we see that there is an increase in the extreme heat stress. We also see for some locations that there is a decrease in the strong and the cold stress, and that there's also like that also the extreme heat stress is reached for the more pronounced global warming. You might think, is nothing happening in Europe? Well, there are changes there as well. But it's because currently there is no extreme cold stress, and on this slide I just show you the 2 extreme classes. So out of the 10 classes, I just took like the extreme cold stress, the extreme heat stress, and all the classes in between are not represented here. So we can also see that the most extreme heat stress class is not reached for the European locations I selected in the study. So what have I learned from this study is that climate data makes it possible to have a far future indication of outer thermal comfort conditions. And it's also important to have a look at hourly data if it's possible, because then you can have a look how the diurnal cycles are changing. And I also saw that for the different locations, there are differences in the diurnal cycle. For example, in the northern locations, there is a much bigger increase in how the frequencies and thermal comfort will change just because of the Arctic amplification of the global warming. And I also saw some limitations. So it's important for, if you calculate mean radiant temperature, that you always use the same formula. And also the biases, I would like to reduce them using a bias correction method. And as I said, this is a coarse resolution model. And of course, we want to know the urban-rural differences and the intra-urban differences. So currently, I'm working on a method to downscale this data. So I'm working now on the European region, and with our team, we are emulating the climate data towards 1 kilometer spatial resolution. And so this is already done for different cities. But of course, you want to include all the cities. And for that, we're currently developing a machine learning algorithm to also have this data. So in conclusion, we will get a change in our outer thermal comfort. I hope I could give you some messages about how to calculate and future directions. And thank you for your attention.
Thank you, Sara, for your presentation.